WarsawJS.
Yep. Hello. Today we're going to have some fun with TypeScript type system. And I know that if your use of types so far was maybe a little limited, to just annotating function arguments with stuff like string or number, then this notion of having fun with the type system might seem a little strange to you. So why don't we start with a little motivating example to see why could we care about type level programming. So here we can see a navigate function that takes in a URL with some parameters and an object that provides values for these parameters. What's really interesting here is that it seems that the type of the second argument seems to be inferred somehow from the URL. So it prevents us from forgetting about passing in a value for a required parameter like here, or it will complain if we try to pass in a value for a parameter that doesn't exist, like in this last example. So to me, that's not only the most type-safe implementation, but it's also the most ergonomic one, because all we need to do is define the URL and parameters once, and everything else is inferred then. So here's the magic that's behind this. And if you don't fully understand what's going on here, well, then don't worry. It gets easier with a bit of practice. Although I must confess that even for me, it takes still a bit of effort to read such complicated types. I guess it's mostly due to the gruesome syntax that we have to deal with, but it's doable. Okay, so obviously you can see that the type system in TypeScript is powerful, but the question is, how powerful exactly is it? And the answer is here, that it's Turing complete. Now, who here knows what Turing complete means? Okay, I see some hands. So obviously you can check the formal definition later on Wikipedia, but for now, let's stick with something like this. We're going to say that a language is Turing complete if and only if for any program in Python that does some calculations, we can write a program in this language to do the same calculations. So it's about the capacities of, well, the computational capacities. It's not about like performance or everything. And of course, Python here is arbitrary. Any regular language will do. So in other words, TypeScript type system is just like any regular programming language. And if that's the case, then why don't we have some fun and try to approach it like it is and test this claim, right? So before we do that, just a little bit about me. So my name is Mieszko Sabo. I'm a software engineer at a software house called Software Mill. I like interpreters, types, all things related to developer ergonomics and developer experience. Also, I have some open source projects related to type level programming. So feel free to check them out on my GitHub page later. And back to our topic. So here I'm listing some common features, some features that are common in different programming languages. So we have arithmetics, functions, conditional branching, variables, loops. And from data structures, we have lists and hash maps. So obviously, if we were designing a like a dream language, we would extend this list. But I'm going to say that this is like this minimal list of features that I would feel that's enough to get stuff done without much pain, right? So during this presentation, we're going to try to simulate all these features with just types. Let's start with arithmetics. Arithmetics on types is kind of this gray area. There's no official support for it. There's no built-in operator to do addition or subtraction on types. However, that didn't stop the community from finding clever ways to achieve that. The first trick will use array lengths to represent natural numbers, and second trick will involve converting back and forth from string to number representation. So let's start by looking at the first trick. So here we've defined a 3 tuples, an empty one with 1 element and with 3 elements. And when we read the type of property length of them, we can see that they're typed 0, 1, and 3. So that's really nice. I guess it could have been number, 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 but it's actually the most concrete, the literal type that's possible. So that's nice, and that allows us to come up with this algorithm. If we wanted to add 3 and 2 together, we could just create an array of length 2, array of length 3, concatenate them, and read the property length of the newly created array. So here's how it looks in code. I'm going to skip over it. You'll be able to read it on your own later. But it's just to show how brief this implementation can be. So here's the actual thing. We create the arrays, concatenate them, and read. And here's an example. When we write, for example, add 4258, it will evaluate to type 100. Second trick, but the first trick is nice, it's brief, but it's also limited. It only works on natural numbers. So 0, 1, 2, 3. Because of course arrays cannot have negative lengths. The second trick is much more powerful. The general gist of it is that we will stringify the numbers that we want to add, then do this kind of school addition where we put 2 numbers. We can think of it where we put these 2 numbers above each other and go column by column and calculate the carryovers. And the thing that allows us then to convert the string to a numeric type is this thing. This infer with extends number. And I believe it was added only in TypeScript 4.9. So it hasn't been for too long, but then we can write something like this. So we have this parse int, and when we have this 42 string, and it will evaluate to 42 number, well, a numeric type, right? Of course, if we passed in something like hello world, we would get never. So in the past, I wrote a 2-part blog post that's kind of this step-by-step tutorial that goes over how you can implement it from scratch by yourself. Here's a link if you're interested. You can scan the QR code or reach out to me later. I'll be happy to share it. But if you don't want to write it from scratch, you can also use something like TS arithmetic, which is a library that implements type level addition, multiplication, etc. And not only it works on integers, it also works on floating point numbers, which is kind of insane. Okay, let's talk about functions. So this is a JavaScript function. And this is a generic type. So we can see that they're extremely similar, and that could be our hint to use generic types to simulate functions. Even better, just like in TypeScript, we can annotate arguments. We can restrict the arguments to be of certain types. We can also restrict the type parameters to be subtypes of some types, like here. And this is an example of how we can invoke these functions, these type level functions, right? Okay, if then else, so conditional statements, it's not going to probably be a surprise that we're going to simulate conditional statements with conditional types. That's how a conditional type looks like. It's very similar to a ternary operator, but with one very important key difference. So the first part is not a Boolean or something that evaluates to Boolean, but rather it's this thing in form of x extends y. And so this is a question whether x is a subtype of y, or in other words, whether a variable of type x can be assigned to a variable of type y. If that's the case, then we will evaluate the if branch, and if not, then we will evaluate the false branch. Here's an example of how we can write our type level if with 3 type parameters, the cont, that's a Boolean, if branch, f branch, we check whether cont extends true, and we proceed with one of these branches. Here's an example. So we assume that each string will evaluate to either true or false. Of course, we're talking about true or false on type level. and it will then proceed with string if that evaluates to true. Okay, now variables. So this is kind of, this might blow your mind. The question is, can we express this with types? And by this I mean like this flow of writing some code, doing some partial computations, assigning them to variables, and then referencing these variables later. To kind of make the instead of writing one huge expression, the idea is to split them into these variables, so it's possibly easier to read. And the answer is surprisingly yes, or maybe unsurprisingly at this point. So the trick is to use the infer keyword in a clever way. So usually infer keyword is used to extract a subpart of an expression in conditional types and to assign this subpart to a variable. But if we use the infer on top level, we can actually infer the whole thing, right? The whole thing that's on the left. So in this case, let's put these two together. So here we have our right-hand value, which is the value, and the variables here, and here is reverse. The variable is here, and the left-hand value is kind of what we're inferring. We do the same with B. So 4.5 extends infer B. We have to, unfortunately, we have to explicitly type these variables. At this moment, TypeScript cannot just infer the types, unfortunately, but maybe that will be changed. And then we can reference both of them, just like here on the left. Of course, so another thing is that if we use this infer on top level, we are guaranteed pretty much to proceed with the if branch. So the else branch will never happen. There's no way that it will fail, but we have to add it anyway to not have a syntax error. So that's why we have these trailing nevers here. So this is the general formula. If you want to write something like this, const variable of type equals value, semicolon, then the rest of the program where we can reference the variable. We can rewrite it like this and into when we are doing type level programming. So we write value extends infer, name of the variable extends type, then the rest of the program, and this trailing never. Is it useful outside of this little experiment? Yes. That's actually how I learned it. So it is it is kind of this common practice for type level library authors to optimize their types. To optimize types, it means to reduce the type checking time, the time it takes the type checker to do the type checking. Okay, so imagine we have some expensive type, maybe it's a recursive type or something like this, and we want to call it twice here with the same argument. So we know that it's going to be the same result. So what we could do instead of this, we could do this expensive calculations once, assign it to a result like here, and then in the if branch, we can reference it as many times as we want, and it won't cost us anything more. Okay, loops. In functional languages, we express loops using recursion. And since the type system of TypeScript is on its own technically a functional language, a pure one, to be precise, that's what we're going to do. So this is like this general schema of how a recursive type looks like. We usually have some inputs. We check condition on this input, and we check whether they extend true. If that's the case, then we return the base case, and if not, then we recursively call ourselves, well, usually with some other input. So this is a function that I'm hoping you're all very familiar with. It's a fib function that calculates the nth number of a Fibonacci sequence. That's very common among programmers, as either as a demo, or either as a demo or like the first function that you write when you learn to program. And right now we're going to conclude this presentation, we're going to combine everything that we've learned so far, all the techniques, and try to write a fully type level implementation of this fib function. So for time, I'm not going to do any live coding now, but we're going to go step by step on slides. So on the right, we have our first approach. So let's go step by step through it. On the left, we need to define a function called fib with a n, that's a number. So on the right, we're going to, of course, use a generic type with a type parameter that's constrained by number type. Now let's move on to this if statement. So we need to write if n less than equal 1, return n. So we're going to use this less than or equal type that in this case, it's imported from TS arithmetic, the library I mentioned, although you could imagine writing such type with one of the two techniques I showed you in the arithmetic section. So we write this, and in TS arithmetic, there is this convention that relational types return either -1, 0, or 1. So in this case, if we want to check this condition, we will check whether it extends 1. And if that's the case, we evaluate to n. So that corresponds to the return n. And now here, there's this expression where we add last two recursive calls of this function. And on the right, it's pretty much the same thing with just instead of using the infix syntax, we use prefix syntax. So we move all this, like this plus operator in front, and the same with subtract. And now if this worked, I mean, I really wish it worked, right? It'd be like, it could prove my point, which I'm not making, but I could make a point that type level programming is fun, it's easy, clean, etc. But unfortunately it's not. And when we try to write it, we will get this type error that this type is excessively deep and possibly infinite. Now, the thing is that in theory, this should work, right? It seems correct, and maybe even it is, but another thing, and that's why I put an asterisk next to the Turing complete, because the thing is that we're still dealing with a type checker, not a regular language. And the TypeScript team made some heuristics or like very pragmatic choices to optimize the type checking performance. And so that, well, type level programming, this esoteric thing we're doing here, that's getting complicated because of that. So we need to be more clever. So how we can solve this? Well, it seems that this big add, fib, subtract, etc., it's just too much for TypeScript to evaluate. What if we could split this into simpler parts and then combine them together? So we're going to use this trick with variables, and here's the formula. So my plan is to extract this fib, subtract, and 1 into one variable, and fib, subtract, and 2 into a second variable, and then add them together. So that's how it's going to look like. Well, like this, it seems less readable maybe, or like more complex, but for TypeScript compiler, it's actually much easier now, because all it does is, okay, here we just infer something, here we infer something, and here we just add these two variables together, and that's all. And in fact, yes, that's going to work. And if we check it, we can do this test, do fib10, and in fact, it will evaluate to a type, numeric type 55, which is a 10th Fibonacci number. So that's it. And here are on this last slide are my recommendation, because what we did was kind of this overview of type programming. And here are my recommendations on how you can maybe learn more about it. So I'm not going to go over it. There's a link that links to my website, which has the same list, but also with some comments. So feel free to check it out. And that's going to be all from me. Thank you very much for having me, and yeah, have a good rest of the evening.
Having you. Thank you.
Thank you. So could you explain or maybe show how is it being transpiled to JavaScript, if it is?
It's not. That's the neat part. Well, no, yeah, it's just types. So as So the way TypeScript works is that we write the types, we use them during our build time. At build time, right, we run the type checker to check whether our program is correct on type level, and then the types are just removed, and we're left with JavaScript. So the removing of types is really simple. We just erase them, and that code gets sent either to the browser, because browsers can only interpret JavaScript, right? Or in case of Node.js, the Node.js, right?
Where's our next question?
In the code examples, one thing that I noticed, because I'm not a TypeScript programmer, was that we used extends, infer, and quote unquote variable name to name a variable, so to speak, and then we did extends type, so that we extract true, and we can go to the to the branch of the ternary operator. I think in one of the code examples, the second extends was missing, and apparently it still worked. Or did I?
Here in this slide?
Let me see. No, not in this slide. Maybe I'm just wrong. If it's required, then.
So the thing is, let me show this formula again. Oops. Okay. Yes, on the level, on the left, we have value, which of course is a type, which might be misleading, but we're just, we're focused on type level programming. So the value is, as you said, we have this infer variable, so name of the variable. And then this thing in practice is kind of like the same as this, because this is a type and this is the type. So this should be the same. But the reason, as I mentioned, the reason why we need to add this kind of redundant thing is that if we didn't, then down here, the variable would have this not very helpful type of type parameter, and that's it. So unfortunately, so this extends here tells what type this should be, and yeah, we need to add this. Because this lets us do something like we infer something if it extends number, for example, and if the value is not a number, then we will go into the else branch. So if we go here, we are guaranteed that not only this thing matches the pattern we're looking for, well, this pattern is everything, but also it's of this type. If I don't think that I missed anything, like maybe here, but here it's maybe not. Okay, maybe I could have added it here, but it's not that important. So it depends on the situation.
Thank you. Did you ask already how many people are TypeScript programmers? How many are using TypeScript?
Oh, good question. I was also interested in that.
Another question?
Yeah. Thank you for the awesome presentation. So I have a question. Your presentation didn't mention anything about the abstract syntax tree. So maybe you were curious previously about it and how to optimize it, or maybe you dive deep into it. Thank you.
How to optimize the abstract syntax tree?
Yeah, the question is overall about abstract syntax.
Okay.
Like, did you try to?
Yes. Yeah. Actually, yeah. It's a nice question. So about, I mean, for me, because I have something to say about that. I have this project called walk.type, and it's a work in progress project. However, what I try to achieve in it is you passed in any TypeScript type, and then it will let you like step by step go through it, evaluate this type step by step, which is something new, because normally the type checker just checks like the whole type is just single expression, so the type checker will check whether the type is correct or not. But what I was aiming to do, since I was writing a lot of these complex types and debugging them is extremely painful, as you can imagine, so I thought that maybe it would be nice if I could go step by step in this type, like, from the top to the bottom. And what I did to do that was write my own TypeScript interpreter, or like I'm in the middle of it, because it turned out to be pretty complex. But the TypeScript, so TypeScript is you can use it in CLI, the TSC, the TypeScript compiler, but also you can import stuff from it, like import something from TypeScript, and it gives you this API that you can use to read string, which is usually like your source code of TypeScript file, and then it will give you the abstract syntax tree, and that's what I used to go to see all the nodes in the syntax tree and evaluate them, so. Yeah, sometimes this is, but this, I think, the abstract syntax tree, and that's kind of important maybe for this case, but not in general. If you're just trying to write types, then you don't think about it. I'm hoping it maybe somehow. Okay. Oh, okay.
Huh? Abstract syntax tree. Does anyone else have any other questions? We're going to probably, okay, we have one more. Go ahead, because it's fascinating. String theory. I feel.
I have a question, since this topic seems like a little bit esoteric and a lot of fun. So I wanted, once again? Okay, so this topic seems really fun, and I was wondering, are you familiar with like the craziest things that people done with TypeScript types? Mm-hmm. I mean, did someone, I don't know, play Doom on it or something like this? Mm-hmm. What's possible?
Yes, so I'm familiar with few such projects. I think the most impressive one I know is someone implemented Flappy Bird with types. And that's even more impressive. Like usually that shouldn't be possible, because as you mentioned, it's a pure language, right? It doesn't do any side effects like rendering or something like this. But what they did, that's crazy, is they write their own runtime in Zig, I believe, and they like had these types that allow them to paint screens, frames, and that's how the Flappy Bird, how they got it to work. And the second thing, I think, if you know GraphQL, there's also a client for GraphQL that lets you like it infers the whole schema. And so someone wrote a whole GraphQL parser in TypeScript types, and it will give you auto completion when you write the things just based on the types. So sorry, not on the types, but it reads the regular GraphQL language, so the string, and then it knows the types of it. So that's also impressive. Okay.
Hey, WarsawJS community, give Mieszko a big hand.